Hell yeah. So I actually start to solve this problem at 1 hour, 5 minutes, and 55 seconds. Alright, hell yeah. So we have statics, and this is the quick version. Obviously we go through this hella, but what I wanted to show was how to do free body diagrams. What I like to do is like chop this ladder out of outer space and then put it just over here. And then what we're going to do is we're going to observe what's happening on Earth, but then relate it to something that is literally in deep space away from every stars, and it just has this orientation. And what we're going to do is apply a force. We know that the ladder has a weight at the center of mass, and so we're going to apply that force. And we know that F equals ma means that if we do apply a force in this direction, we should see movement in this direction, a change in velocity. But we don't. We go back to here, and then so in this direction, back to Earth, we don't see any motion. We don't see motion this way, and then also rotation. So we have to go back to here, and we have to apply forces in this direction. We see that the only two contact points are A and B, so we must have maybe a force in this direction to balance that out. And then here's the second aspect of it. When it comes to, in this problem, friction is neglected. So every surface, even this point, I would treat the point like a wheel, like almost like a wheel or a pulley. And then this point right here, what we're going to do is we're going to treat the ladder like it's a wheel. You know what I mean? So you have a wheel right there. And what we know about wheels is you can only have a forces perpendicular to the contact points. So here's the force at B, and cool. So we have this force at A, up against this wall. And I even come down here to show that, hey, if you actually did have friction here, you could set up the ladder where it's not touching the wall, because because the weight of this thing isn't driving it into the wall. And I do talk about that kind of in the video. It's just like, well, but anyway, but we don't have that. You kind of have a wheel right here. And then so what I show is that you do have a force in that direction, and this has a component this way. So now we come back to our diagram in outer space. Now we have a component that is in this direction. And if we do have a component in that direction, then that means that this thing is moving that direction. But we know that's not true because we go back to Earth and be like, no, it's still stationary. So there must be forces in this direction. And the only other place to have a force is at A. Because one of the things with free body diagrams is like, hey, there's nothing touching that section. In here, there's nothing touching that section. So the only places that you can actually have forces are where things touch. And I guess, if you have something on the ground, heck yeah, you can have a force in that direction. If you have friction, you can have a force in that direction. If it's actually welded to the ground, you could have a couple. And you could have these in the XYZ, and you could have this couple in the XYZ. You know what I mean? So that's kind of the advanced, but now back to our problem is like, so maybe we have a force this way to balance that out. And then the third aspect of doing statics is looking at the center of mass. Because if I have forces through the center of mass in this thing in deep space, cool. It might be traveling a certain direction, but it's not rotating. But the second I have forces that aren't going through the center of mass, hell yeah, this thing is going to rotate. And we just showed that maybe we have a force down right here, and then also we have this dude, and he's going to be like up here. And so we have, and then we have these. So we labeled in all our forces, and now this is the trickier part. Around the center of mass, just to see if this thing is spinning, we have to, and what we do is we say it's not spinning. Due to statics, we're like, okay, this thing isn't rotating this way, it's not rotating that way. So that's where we have to use moments. Moments are force times distance. We use them like we're opening a door. If we hit the doorknob with a force, hell yeah, we have a big distance. But let's say we just put a little nubbin right there on the door. Well, like you would have to actually put in a huge force like on that little nubbin to get that door to open. And so, and let's say you had a couple little nubbins like this, and you have a force here and a force there, and you don't want the door to open. So you want to put and on the doorknob, you want to prevent the door from opening. And so, well, you have to have this moment, has to equal both of those. And so the definition of a moment, or the magnitude of a moment, the actual number that we ascribe to it, is kind of its leverage. It's the force that's applied times that distance. Those two numbers together are what has to equal. So we come back here, the dude is this distance away, that's going to be a positive, making it spin this way. Coming around the circle, maybe this one up against the floor is also making it spin this way. And then let's go to these ones. Oh, and even this one up against B is making it spin this way. So this one down is actually making it spin in the negative direction, and then this one against the wall is spinning it into the negative direction. So booyah. But that's it. But I think the moments are a little bit harder to visualize, but I do like the idea of still taking this thing, putting it in outer space, and showing that, hey, we at least have a force of gravity. It has to be balanced. And then showing that, hey, when we balance it, we're going to get a force in that direction, and those have to be balanced. So forces in the X and the Y have to be balanced because this thing's not moving this way, it's not moving that way. And definitely it's not rotating. It's a little bit harder, but we go through this whole problem. So sit back, relax, and enjoy. It's not a very good video, but thanks for joining me. Alright, hell yeah. So we have engineering statics. And what we're going to go over today, this might just be part one for this problem, but we want to go over free body diagrams. And I'm going to try to do this for more videos because setting up the free body diagram is the hardest thing. So what we're going to do is we're going to draw this ladder. And I think I got a good method for describing what a free body diagram is and how to kind of analyze it. So what I like to do is just pretend like this ladder is in outer space. And I've also come up with the idea that you want to put it in like the deepest reaches of space that you can think of, away from every star, farther away from, basically like it's the only thing in the universe actually, where there's no gravity or anything. Okay, and then what we want to do is kind of flash from this scenario and then back to Earth. Okay, and but the first thing we're going to be looking at this in outer space is that this does have mass. It's made up of atoms, and so we can say that it has mass. Okay, so now we're going to go back to Earth, and one thing, especially when it comes to statics, is that we know we have a huge Earth underneath us, and then we have, we want to build like a building, and we know that that building has mass, and then the Earth has hella mass. And we use the equation that there's a force, the weight of something. You can say weight, or the force of gravity is that equation, gravitational constant, the mass of the building, mass of the Earth, and then divided by the radius of the Earth squared. Now this is also what we usually say if, like, hey, the building's on the ground. In engineering and statics and physics, you'll just draw an arrow and you'll just say mg. You know what I mean? But I think it's good to know where this mg comes from. This would be the weight, mg. This is the m right there. But then these three terms, those are going to equal that g. That's going to be 10 meters per second, or 9.8. Okay, hell yeah. So that's kind of the second thing when we flash from outer space back to Earth. We're going to say, well, this ladder, we know, has a force on it, and I'm just going to put the force of gravity, and then you know that that's the weight, or that's mg, and I guess I can spell that out, but who cares? What we really want to go back to is the basics that Newton discovered, that there's a relationship between force. I should say, if you have a mass and you apply a force, you should see some sort of acceleration. So that's F equals ma, is that this ladder has a mass, and then we're applying a force on it. And so this is why I want to go back from, the two different perspectives of outer space and then Earth, because we want to... Alright, let's just get to it. Let's say I did... So we know that this this ladder has a mass, and we have an earth underneath it, and we're going to have a force on that ladder. And, you know what I mean, this ladder is actually made of a bunch of chunks of mass, and each of these masses is going to be pulled down towards the center of the earth. And the resultant of that is putting that weight at the center. But that's not for this video, but just know that that is a, what would you call it? I don't know if it's called a proof or like a, but it's a simplistic version. Like, you know that this is representative, the weight being in the center, for what we're going to be doing, but just know that it's accumulation of all the forces along here towards the center of the earth. Okay, hell yeah. So so now that we have at least one force on this mass in deep space, is that we know that it should be moving in this direction, because we identified a mass and we identified a force, and so we should see a change in velocity every 1 second. That's the definition of acceleration. The units on acceleration are meters per second per second. But then we don't. And the only reason that we shouldn't see, if we go back to Earth, and this is kind of where I kind of do eyeballs, and we see that this thing is not moving. It's not moving in this direction, and it's also not spinning. Okay, so so now let's go back to outer space. So the only way this thing can be stationary is if there is a force upward that's equal to this weight, this mg. And we can put, and the cool thing about the way the physics works is we can divvy this up. We could put two forces. We could put a smaller one here and a smaller one there, and then maybe adding these two up will equal this weight. And so then we go back to our diagram and maybe like, hey, where's the points of contact? So I have a point of contact at B. I'm just going to say this is point B and this is point A. And so maybe we have one right there, and then we have one right there. Cool. So we're going to say that those two forces have to equal this force, because this thing is stationary. And cool. So that's kind of just one aspect of and the neat thing is they don't have to be in line. You know what I mean? So this force could be over here, this force could be over there, but just in general, this thing is now not moving in this direction. Okay, and then that brings up the next idea in statics that's very basic, is that the sum of the moments have to equal 0. You know, if something is stationary, the sum of the moments have to equal 0. Man, and this is just a learning experience for me, because it's just like, well, what's a moment? Well, that's a force times distance. And let's say the sum of the moments weren't 0. What would be the equation for that? Well, we would come up here and see that force is mass times acceleration, and then we would have times this distance. So we would have that moment, like if we just had one of these, you know, let's say we just have this, well, let's do the problem like it is. So we have, man, actually, I'm going to take a step back, because we have this force. So let's draw the ladder like this in outer space. And we know that the weight of the ladder towards Earth is a bunch of little chunks of mass. So why are these little chunks of mass equal to just one big weight right in the middle? And then why can we put this in the middle? And then also it goes back to the moments, is that we have a center of mass of this. The thing can be balanced. So if we have a teeter-totter and it's we have an equal length on both sides, we could set up a scenario where we can balance this thing, and that means that there's no moment, there's no force over here times a distance creating a moment, and then a moment would create acceleration. Alright, hell yeah, I had to pause because this is where I kind of want to put my focus for other videos, is that this equation is for kind of a linear motion, but what I'm trying to show is that if we do have a moment, we're going to have a rotation, and rotation is for sure not linear, where you have just all sorts of things going on. The mass at the end is going to travel faster than the mass, and the mass in the middle is just going to be kind of stationary. Mass out here will be going slower, but that'll be for another video to relate linear speed. But I can do it. I was just like, well, let's not take a moment. So we're going to make this ladder even simpler and just say it's a pivot with a string or a massless rod, and then a mass out here, and then a force right here. And so kind of here's our teeter-totter or our pivot, here's our distance. We do generate a moment that, so some of the moments we're going to have F times D, and that's going to equal this mass, its acceleration. The acceleration is going to be kind of in this y direction or this linear direction, and then we would have times distance. So if we wanted to know the acceleration in the y direction, we would rearrange and we would say the acceleration is just force of d divided by md, and then we would just be back to F over m, which is F equals ma, just rearranged. Acceleration, linear acceleration is just F divided by m. But where the continuity happens is that what you would want to do is find out the angular acceleration. So you would have alpha, and it's going to be in radians per second. And how do we convert from radians, or what the hell is a radian? Well, I always say radians times radius gives you something normal, and that is going to be your linear acceleration. So if we can substitute the angular acceleration times the radius in for here, and let's do that. We would have F times D is equal to m alpha. Now this is going to be, the radius is d, so we're going to have d squared right here. And now we could solve for the angular acceleration, which is fd divided by md squared, which would be F divided by md, which is basically just the acceleration divided by the distance, or another way to say the acceleration divided by the radius, and that is the definition of angular acceleration. Radians times radius gives you that linear acceleration. Okay, hell yeah. So that was just a tangent, but it's just like, well, I just don't want to, gloss over that. So maybe this is kind of a learning video. I really wanted to just get to it, so maybe we'll have the get to it part right at the beginning. Maybe I'll do like a 1 minute, because honestly, it's as simple as like, hey, this thing is stationary in outer space. Then we put this force. It should be traveling this way. We got to apply two forces that way. Okay, now it's stationary. Okay, now, but so that's kind of where we're at. But these forces are off center from the center of mass. So if we did have that, if you just had a ladder in outer space, and then you go up and put a force over here on it, well, sure. The cool thing about this is the center of mass will travel. F equals ma applies. F equals ma. So the acceleration, we do have a mass here. We applied a force. We're going to get a number for the acceleration, and that is going to be in this direction. Let's say it's the y direction. So the force in the y is equal to the mass times the acceleration in the y. But you can see that this thing will also be rotating. It's because the sum of the moments, let's say about the center of mass, well, we're going to have a moment. And then that moment is going to generate. If the moments aren't zero, you're going to generate a spin. So hell yeah. So that's that. I guess yeah. I'll get better at explaining that. But just like we had this, just like we have this ladder that's not moving this way or this way. Hey, the acceleration is zero, and so that means that what you would say is the sum of the forces. We have a force down, it has to be matched with a force up. Same thing, if we don't see it rotating, the sum of the moments have to be 0. So I identified a force in the center of mass, but then I identified 2 more forces this way and this way. So back to the problem. This is kind of where we're at. Is that we can see that these 2 forces are going to make this ladder spin. So then what we need is 2 other forces that make the ladder spin the opposite way. You know what I mean? And then you go back to your problem. And I would do this. I'd be like, well, is there anything? So now I would say, like, I don't know. I'm trying to just develop a style where you can just easily tackle a free body diagram. One, get the thing in outer space, and I guess I didn't do this, is that you really want to chop it out of the problem. So I'm just going to chop that whole thing out. And now we come to the other part that's useful, is like, hey, is this ladder touching anything on Earth? And you're like, oh, yeah, it is. It's touching something at B, and it's touching something at A. And this will be for a separate video, of like, hey, let's go over like what it means, like what's going to happen if things are touching. So in this problem, in all statics problems, is like, hey, nothing's going to happen until it starts to move. You usually have that as your problem. It's just like, hey, this thing is totally balanced, it's not moving, but as this guy climbs up the ladder, at some point it's going to start moving. So any corners, I would just make like a strong pivot. You know what I mean? Just actually make it like it's a door hinge. And that's going to be kind of easier. And be like, oh, okay, so we have that going on. And then over here, and I guess I should say that any hinge or any pivots in statics will have, what happens is that you can pull on this pin in any direction you want to. And if you do pull on this pin in any direction, let's draw it again, it'll always you can always break it up into a component. So let's say we do pull this way. Well, it's going to have a component in that direction, and it's going to have a component in that direction. And then I guess the other thing about contact points is that they always act perpendicular. So if you do have this point, the only way that you can actually brace this ladder is to actually be what we call normal, or just perpendicular. I think perpendicular would be a good term to use. But we can only push perpendicular to this ladder to kind of hold it in place. Usually all these problems, unless they say otherwise, they're frictionless. So there is, and that kind of maybe throws you off. You're just like, well, if it's a totally slippery surface, like if this is just made of ice, you're just like, how does that change things, or does it even make sense? So we might talk about that in a second, but let's go over to point A. And if it's frictionless, so there's no friction may be neglected. What I would do is turn into any of your contact points as just like a little wheel. So draw a little wheel, and then when you do that, you see like, hey, I have a contact point there, upward, and then I have a contact point over to the side. So here's my 2 contact points at A. So now let's kind of draw these in. We can at least draw that we have a force at A. And let's just call that good for now, because, and let's go back to our diagram. We had this force in this direction, and so it was going to travel this way. We knew that it had to have at least one force in this direction, and we see that it has 2 contact points. Both those are going to apply an upward force, and then we say A is going to apply a force. I want to get into this in order, I guess. So, but I mean, you could do it either way. So we said that, hey, this thing was gonna rotate this way due to these 2 forces, and so we need a force on it that actually makes it rotate the other way. And so we can see that this force at A does. It makes it rotate the other direction. These 2 make it rotate that way. Okay, so now maybe, yeah, so this force is useful, it can be balanced. So let's go back to B and actually put, we're going to say B is this perpendicular force, and we're going to say it has a component this way. This is how I like to do it. I like to draw my, like if I know the direction of the force, you know, kind of make it in bold, and then do dashed lines and an open arrow to show the components. So we're gonna we can say that this is by, we can say that this is bx, and this is over here ax, and then this will be ay. And I don't know, I was like, even just doing that probably just made it hella confusing. Sometimes like putting letters to things can make it a little bit overwhelming. Alright, so, but now we're going to put this reaction at A aside, and we said, so let's go back to kind of start over. We have this in outer space. We know that it has a weight on it that's traveling in this direction. We know that it's not moving this way, so we have to have forces upward. We see that those could happen at A and B. And we're satisfied that, hell yeah, B can be an upward force and A can be an upward force. And this is how I initially started this problem. It's like, well, I knew that a point right here has to be at an angle this way. So if we did that, I know that we can have an upward force at B. But I know that I also have, so that's this component. But I also know that I have a component this way. And so that's this force. So again, let's put this force aside. All we've done is put a weight on it, and we know that it should be traveling this way. We observe that it's not, so we have to have an upward force this way. Those forces could come from A and B, but we know that point B sure can provide an upward force, but it can only do so at an angle like this. So it also is going to provide a force that way. So that was kind of the long way of saying, hey, we actually have a force this way on this ladder. So if we went back to our, draw our ladder in outer space, hey, now we actually have a force this way, from that point B. And if we have a force this way, it should be traveling across the universe that way. F equals ma, it's going to be, it has a mass. F equals ma says that we identified a mass, we identified a force this way, and we should have a change in velocity every 1 second. So it should be increasing in speed across the universe that way. But we know it's not. We go back to Earth and be like, no, this thing's stationary. So we must have a force this way to counteract that. And so, so then we can see that, hey, that's going to be down here. We see that this contact point hits this wall and this wall. And so we're good to go. And so now, and we could even, I'm going to take a little break because we could say, hey, let's say this wall did not exist. And we have a ladder, and then we have of this, and we're going to say all slopes are, or all surfaces are frictionless. And you can't even set this ladder right here. Let's draw it like it should be. And so we're going to have this weight right here. We have this, and so let's do our free body diagram. So we have our ladder in outer space. We identified a force down with a weight. We're going to say this is point B, and we have point A. So we know that we have to counteract this force because we know this thing's not traveling across the universe this way. So we can put an upwards at A, and then at B, for sure, we're going to have a little bit of upwards, but we're going to have a force at this angle. And so that's going to have an upward component and an over component. So now, sometimes it's good to just draw your diagram again because we introduced a new, we started with just a force down. We're like, okay, so this thing should be going this direction, but we know it's not. Back to our observations on Earth. So there must be forces upward that counteract this. There is. And but out of that, we get a force to the side. So sometimes it's maybe do just a little side diagram and be like, whoa, we have an actual force to the side. So we took this ladder, put it in outer space. We have a force to the side. We must have but we know it's not traveling this way. We go back to our problem. We know it's not traveling that way. And so we say we have to have another force to counteract this. And again, what we say is that the counteracting force does not have to be in line. It can be anywhere on this. We could have a force up there to hold that. We could have a force down here. And so so we see at A, we're going to have a force down here to counteract that. Okay, and so that's kind of just the idea of the forces in the y direction, the forces in the x, and how this isn't traveling this way or this way across outer space. But then the other aspect of this problem, so let's go back to this, is that it's not rotating. But when it comes to these statics problems, they're static until something happens. So in this case, the something happens is like, hey, this ladder starts to, like when this ladder falls, this point A, or this part of the ladder kicks up, and you're going to have an air gap, underneath the floor. So this problem is basically says like, hey, this reaction right here, that's going to be 0. You're going to have 0 force, 0 newtons right there. Alright, but before we get into the actual problem, let's go back to our free body diagram, because we have to make sure that the sum of the moments are 0. So let's see. Yeah, let's grab a new sheet. So we have bx, by, and then we have ay, and then ax. And I'm actually going to draw this just one more time. So we have the weight. We have at B, we're going to have a component this way, bx. I just wanted to darken these in. by, and then we have ay, and then, oh, this is this direction, ax. And we're going to say this is the center of mass. I'm just going to put that as point O. And then we need to sum the moments about O. So we see that, we want to know if this thing's rotating this way or rotating that way. So this force that goes through O, the weight of it, doesn't cause any rotation. So we kind of went over that. But all these forces that are not in line with O at all, they'll cause a rotation. So this upward force right here is going to cause a rotation that way. This upward force right here of AY is going to cause a rotation that way. This force right here is going to cause a, that's also going to cause a rotation that way. So this force right here, AX, the force against the wall, is the only force that's going to cause a rotation that way. And so these have to equal 0. So like, you have 3 arrows to the left plus the arrow to the right. Those have to all equal 0. And then so, and they just have different units on them. Just as weight has like units of like, force and newtons or pounds, moment is proportional to like how effective it is. Hey, we might have a pretty strong force by, might be like a lot of pounds or newtons, but hey, its distance isn't very far away. So it's the equivalent of, like here's the door handle, and let's say that's point A, but then here's point B. Maybe we have a little nub sticking out, and you're going to try to open the door. Here's the hinges. You're going to try to open the door at point B. So you apply a big force, but it's still not very useful. You know what I mean? You could apply this a smaller force at A, and it could actually be more useful. So the usefulness is going to be the quantity of that moment. You know what I mean? So moment is a force times distance, and so so hell yeah. So this is going to be, so By is going to just visually, you're going to have. Alright, so you're going to have that force By times, this distance. I'm just going to call it D1. And then you're going to have plus Bx, and then it's going to be this distance, and we'll call that D2. And then plus, we're going to have this distance, Ay, D3, plus AY D3, and then that's gonna, and then we're going to oh, and the other thing, so these are going like in a particular direction. You can use right hand rule. This is going to be a positive direction. You're kind of like opening the door that way. This one is trying to close the door. So this one, so you know, even though you're editing them, this is a positive, positive, but this is a negative. So positive plus negative is equal to 0. The other way to sum your moments is like, well, hey, I identified that these are positive, this is a negative. I can actually just set these three have to equal this one. So the equation could be that direction has to equal the one going in the opposite direction. So I'm going to add those three, and that has to equal that one. So if we did that, I could just say that's equal to this AX and then D4. So that would be this dimension right there. Alright, hell yeah. So I got some more paper, and we're going to turn this into a longer problem, because this problem, I really didn't like the picture that was drawn, because I want to test my assumption, because if all this is a frictionless surface, I kind of had this idea. Well, I mean, I should just get to this, is you wouldn't be able to put this ladder in here and make it stay. Or what was I gonna say? Oh, yeah. The whole thing of this is reliant on this person being right here at the start. Like for whatever reason, you would have to put this ladder into this position and then have this person weight the ladder on this side and then start walking up. So my impression was that this X, the distance where this ladder is going to fall, has to be on this side of point B. So that distance has to be less than 1.6. So less than, definitely less than 1.6 meters. But then, you know, especially when a problem gets drawn where you're just like I don't know. I don't like when they draw something that looks nonsensical. Because it messes with your mind. So back to a teeter-totter, if I have an equal space teeter-totter, hey, that's going to be balanced, we can do that. But if I have a teeter-totter that is longer on that side and then shorter on this side, I can't draw that picture. You know, if this teeter-totter has the same amount of mass, and here's the ground, this thing is going to hit the ground. You know, it's not going to be a statics problem. You're going to have dynamics, because we have more force over here than we do over here. And you can even simplify a problem like this by just putting all the weight at the end, and then so we would have like point A and then B. So you would have mass A, mass B. You would have more force over here. Force of A would be bigger than force of B. And you would have, it would fall that direction. Alright, so what I want to do is I want to set up the problem where the guy doesn't even, the guy is just out of the equation. We just have the weight of the ladder. And even with this configuration. So with this triangle, this is going to be a 3, 4, 5. Yeah, I don't know how you're going to be able to see that, but like the 0.4 meters 3 times is 1.2 meters, and then 0.4 meters 4 times is 1.6. So this would be 0.4 meters 5 times. This would be, this distance right here is 2 meters. We have a 5 meter ladder, so the center of mass is going to be at this 2.5 meter mark. Okay, hell yeah. So let's draw our free body diagram. And so we have the halfway point. We have oh, and then so this is going to be our weight. The weight of the ladder, what does it say? Weight of the ladder is 20 kilograms. We're going to say 20 times 10. That's going to be 200 newtons. We're going to have the angle here. And this is interesting. Sometimes it's easy to get it, with angles. You can just be like, heck yeah, I know I know if this distance is 2 meters, I know this side is going to be 2 times sine theta, and this side, this distance is going to be 2 cosine theta. That's useful. Sometimes it's kind of tricky when they give you this setup. What this setup says is that, well, let's talk about what sine and cosine means. Sine means the percent of this distance, the hypotenuse, in this direction. So if I have 100 meters here, and let's just draw a 30-degree triangle. So this is 30 degrees, and this is 100 meters. Well, sine of 30 is going to be 0.5, so this would be 50 meters. And sine of 30 being 0.5, that's basically saying like 50% of that hypotenuse is going to be in that direction. And so we can get that ratio, that percentage, by taking this side 1.2 and then just dividing by the hypotenuse. So we would divide by 2. So we would have 1.2 divided by 2. I would make this 0.6 divided by 1, and then you would just see that that's going to be 0.6 or 60%. So we have 60% of this distance is going to be in that direction. All right, hell yeah. So let's start drawing in our reaction at B, and then we have our reaction at A. So we have, AY, and then this direction is AX. B is going to have two components. It's going to have that component that way, and then the vertical component. And right here, we're also going to have a 3, 4, 5. And so this is where my mind, it's really hard for me to see this. So what I like to do is, like which one is 3 and which one is 4. Obviously the hypotenuse is 5. But what I like to do is this. I like to come in and do a smaller angle, and then know that if I go up at a perpendicular, so now I know that this is happening. So this is a perpendicular angle. If I said that this was 3 and this was 4, then over here this would be 3 and this would be 4. So especially when your angles are close to 45, like a 3, 4, 5. So let's do that. So we said that this was 3, this was 4, and then we draw in our perpendicular, and then we can say that this was 4 and this is 3. Okay, hell yeah. So I'm gonna. So there we have it. So we have BX is going to be, and again, what's so if this side was 60%, this side is 1.6 divided by 2. That's going to be 0.8 divided by 1. That's going to be 0.8. That's 80%. So I think it's useful to know that when you're dealing with 3, 4, 5 triangles, you have 60% on this side and 80% on that side. And the reason why a 3, 4, 5 triangle works out is because if you have 0.6 squared plus 0.8 squared, you get 1. So you get 0.36, and then you get plus 0.64. So, 8 squared is 64, 6 squared is 36, 0.36 plus 0.64 is 1. Okay, hell yeah. So we can see that this is the 60% side, so we have 0.6b, and then this is the 80% side, so in the by direction we have 0.8 times b. Alright, sweet. And, okay, so now we're going to do our sum of the forces in the y direction. So we have this 200 down, so we're going to do negative 200 newtons. We're going to add it to 0.8 b plus ay. Cool. That's going to equal 0. So that was sum of the forces in the y direction. We're going to sum the forces in the x. And again, this is forces in the y is mass times acceleration in the y. We don't see any motion in the y, so we observe no movement in the y direction or the x direction. So let's sum the forces in the x. We're going to have, and this one's going to be fairly simple. We just have this 0.6b plus, well, I guess it doesn't give us anything. And then I'm going to say minus AX is 0. Okay, so oh yeah, I totally forgot. And then we have, so that was, it's not moving this way, it's not moving that way, but it's also not spinning. So now we have to sum the moments, and we're going to sum the moments about there. And you can sum the moments actually about any point you want. So honestly, it would probably be better to sum the moments at B, because if we do that, you know, they just go away. And then we just have... or probably summing the moments at A is actually better, because we just showed that we really don't know what these reactions, or I don't know. Yeah, that'd be fascinating. Maybe let's just sum them at the origin, because that's the center of mass, so we're going to sum them, or basically the center of mass right here. That's where we're going to sum those forces, and it might as well. And, alright, heck yeah. But we're not going to sum we're not going to use both components bx and by, because we know that a perpendicular distance to B is just 0.5 meters. So we have 0.5 meters times B, and that's going to be a positive moment. And then at A, we're going to have... bummer. Yeah, this is where this problem, you know, yeah, gets sucky, because you're going to have to figure out where you want to sum your moments. Bummer. Yeah, so I guess we need to just to figure out the distance over to this this point. So we know that this is 0.5 meters. Hey, we got a 3, 4, 5 triangle. It shouldn't be that hard. I don't know why, like, I kind of freak out. But I just need to know this distance. Well, we said this is going to be 80%. This is 60%. So we're going to have 80% of 0.5. Cool. So we're going to, and that's going to be a positive moment. Or where are we at? We're summing the moments about... Oh, I needed to know this distance because I need to add it. The next one, if I'm summing the moments right here, I got B, but then I need to sum the moments of AY and AX. So we're going to sum AY, and that's going to be a distance of 1.6. So we have 1.6, but then we have to add it to 80%, 0.8 times 0.5. Cool, so that's that total distance from there to here. And then we have AY. So that's force times distance. Then we do it with AX. So yeah, I'm not doing it the easiest way, but it's useful because we're on the fly figuring out these distances of these sides using the 3, 4, 5 triangle. So this distance right here is going to be 60% of 0.5 added to 1.2. So the same thing, 1.2 plus 0.6 times 0.5, and then that's going to be AX. Alright, so we got 3 equations, and we have 3 unknowns. And in this scenario, I just want to know if it's going to tip over. And how I would know if it's going to tip over is if AY has to be negative. AY should be a positive value, kind of holding that weight. But if AY is a negative value, you know, like it's a spring trying to hold, like push it down, then I know that I can't get that and it's going to tip over. So I definitely want to solve for AY. Okay, so yeah, this looks brutal. So let's kind of clean this up. We have 1.6 plus 0.8 times 0.5. Okay, so that's 2. So we have 0.5b plus 2ay. And yeah, could I have done that? You know, this distance was going to be, oh, it's 2.5. So 2.5 times 0.6 and then 2.5 times 0.8. 2.5 times 0.8. Yeah, I could have done that way easier. Yep, so this one is going to be 1.5. 1.2 plus 0.6 times 0.5. So we have, and I got the sign wrong. This has to be minus. So if this is the center of mass, this force is going to cause rotation that way. This force is going to cause rotation that way. This force is going to cause rotation the other way. So it has to be minus 1.5 AX. Okay, and then that's going to be equal to 0. And we're trying to solve for AY, so let's just solve for this for AY right now. So we're going to say AY is 0.75 AX minus 0.25 B. So I did a couple steps because I kind of just want to get on with life. But I took this over here, 1.5 AX, but then I divided it by 2. And then I took this over here, negative 0.5, but then I divided it by 2. Cool. And now we can get AX in terms of BY, which AX is just 0.6B. So 0.75 times 0.6 is 0.45B minus 0.25B. Okay, sweet. So minus 0.25, and we have 0.2B. Cool. And then we can solve this for B. Yeah, maybe that was a dumb way to do it, but probably. But yeah, we're going to solve this for B, and we're going to get B is 200 divided by 0.8 minus, so that took this over here, divide by 0.8, take this over here, minus AY divided by 0.8. So AY divided by 0.8 is 0.2 divided by 0.8. That's going to be 0.25. So this is going to be negative 0.25B. Oh, wait a minute. I need to, if this is B, I need to FOIL this through. So sorry about that. Well, just 0.2. Yeah, so if this is, I just need to multiply by 0.2. So we have 200 divided by 0.8 multiplied by 0.2. So that's going to be 50 minus, and then we have 0.2 divided by 0.8. 50 minus 0.25. So we have 50B minus oh, my bad. No, yeah, we're foiling this in as B. So the B goes away. Holy hell. Oh, this is an awful video, but we're doing it. So, yeah, so we're going to have 50 minus 0.25 AY. So we have AY plus 0.25. So we're going to have 1.25 AY is equal to 50. And AY will be a positive number. Alright, so I think my conclusions, yeah, this is interesting. It's because you have a reaction here that's helping. Yep, so this isn't like a teeter-totter. That fascinates me. And that probably makes sense. Is if I have a glass cup made of, like, lined with ice that's very slippery, and then I put a metal rod in there, I can get the metal rod to stick out farther than if it was just a teeter-totter. So holy hell. So I guess that's kind of what I learned from this problem. intuitively, I couldn't understand that, because I'll tell you why. Because this is another problem that I was thinking it was similar to. So like at Walmart, you have pallets, and then you have you have people that are just moving heavy pallets all day, but you have a floor that is dead flat. So sure, this has mass, and sure, you have to have a component. If this is your vector on your force pulling this, you have a component this way and you have a component up. But anyway, so the driving component, that component is F equals ma. That component is changing the velocity every 1 second. So you apply any force, you're going to move this. So that's kind of interesting. As long as there's no friction in the system and you have a level, it doesn't matter how massive this pallet is, it's going to take a minimal amount of force to move it. And this was so interesting to me because I think at Walmart, I see tons of people moving really heavy pallets, but I don't think there's any motor. I think they're actually just pulling the pallet along at their own, with their own force. And so it might take a little bit of time to get that up to speed. But once you do, you should be able to, to carry that speed. I don't know. Yeah, it feels like they're not motorized. But now my question is, let's say you had this. So you have 2 wheels there, and you also have a ceiling like this. And what I wanted to know, and I didn't draw it how I wanted to draw it. I wanted to draw it like this. So you have a heavy pallet, and then you have heavy springs right here, and then you have a ceiling. So the ceiling is totally level, and then you have here your floor is totally level. And let's say you have the mass of the pallet, and then these springs are applying a downward force. So you actually get a normal force here. You're pushing up against the ceiling and you're pushing against the floor. So the normal force against the floor is going to equal mg plus the normal force on the ceiling. So this is the normal force on the floor, mg plus the normal force on the ceiling. And that's the other thing from a free body diagram. You're just like, well, shouldn't there be the same force on the ceiling as the floor? It's like, no, because you take off the springs, you're still going to have a force on the floor, no force on the ceiling. Just because you inserted a spring, that spring force is only due to the change in length of that spring times a spring constant. Okay, but in this case, my question was, like, is it going to take any extra force to pull this system? And as long as there's no friction, as long as you're coming up with a frictionless floor that I've just kind of oversimplified using wheels, then no, it's going to take the same amount of force to pull this. It's not going to feel any harder to pull this scenario than it is to pull, just the pallet across the floor. So from that idea, that's where I maybe confused myself on the fact that you have a frictionless cup and then you have a steel rod in it. That I was just assuming that it acts like a teeter-totter, just like that. Where if you have more weight on this side, and then you let go from a stationary position, this thing is going to rotate that way. But with the cup, you are applying a force this direction. And then further looking at this problem is that you're always going to have a force pushing this down into the container. If it is a glass with a steel rod in it. If you pull out on the steel rod, that's one thing, but you would have to have a force in that direction. And because the component of the weight is downward, the component of the weight is never in, it's never on this side. It's never going in that direction. So the weight is always driving this thing back down into the cup, and then therefore you generate this this force against the wall. And even though it's a frictionless surface, this force against the wall still prevents the rod from lifting up out of the cup. So yeah, that is fascinating. So it's very interesting that this thing is probably drawn to scale. And so let's tackle this. You know what I mean? What a long, boring video. But it's good because I had some misconceptions, and I kind of just disproved them. So that is kind of cool how it's like, don't solve their problem, run through your own problem and solve that. And you know, because then you could get rid of this dude and just say, hey, how long of a ladder could you put into this little well where it won't just tip over? You know, so you could also do that problem. We're like, hey, let's change the length of this. And then, so let's do that. But that gets into the point of like, well, what happens when this thing tips is that this reaction, AY, becomes 0. It is no longer providing a oh yeah, that's interesting. I mean, I was going to say it's no longer providing a torque in this direction. Well, that's true. But what's happening is this weight over here is providing a larger torque, a bigger torque in this direction, where this force in this direction is providing that opposite torque, this negative torque, that, you know, at that point, those are not going to be balanced. This is going to be bigger number than this. Is not going to be 0, because to make it 0, you would have to have, Oh yeah, that's interesting, because analyzing this is that if it is in a stable position, like you get the ladder in there, you get the guy down here, this force right here is actually going to be quite large. You know what I mean? So you can say that off the bat, hey, this force making this thing spin in this direction is going to be the larger force. And so the only way to counteract that, and you really don't, even if the guy's just kind of just right here, you only have a small torque that way. And then the ladder, it's not much weight, and the center of mass is really close to this point, so you have another small force that way. So you have a small positive, a small positive. But here we just said that we're going to have a huge negative force, because in this scenario you have a lot of force up against this wall. And that's that is cool, because that literally goes back to the free body diagram of like putting this thing in outer space. Like, hey, we're gonna jam a huge force here. This AX is going to be quite large, and it's going to cause a huge rotating moment this way. So and so that has to be balanced. And the only so let's just focus on this rotation. The one that's gonna, because these aren't going to help. So if it's rotating this way, like these forces aren't really going to help the rotation. Where the guy is and then the weight of it are going to be small, as we just said. So we need something to balance this so it's not spinning. Because we observe that this thing, you know, when it's balanced, it's not like rotating. We're observing that. So we chop it out of, chop it, put it into outer space. We say it's not spinning, but we have this. We identified a huge force that is going to cause a spin. So what gives is that this reaction on the floor, this AY, is also sufficiently big and sufficiently far away, and this is going to cause a large rotation that way. So that's where you can see that this moment is going to basically equal that. This moment plus these other two moments are going to equal each other. All right, hell yeah. So yeah, that was kind of interesting, and that's where Because then that's where this problem kind of gets interesting. Because when it does fall, like what we're saying is that, hey, we still might have this large force up against the wall, like pushing up against the wall. Like that force still might be large and exist. But we're saying that this force on the floor goes to zero. So this thing goes away, but we still might have a large force up against the wall that's causing this thing to rotate that way. And again, like if it's falling this way, you know, obviously the ladder is going to fall that way. So we have to say what gives. What changed? Well, it's the dude. The dude weighs hella, and then he went farther away from the, you know, this distance got big, and the force on this is much larger, you know, than yeah. So this is going to cause that rotation this way, and now in this scenario, this force at some point is going to equal this force, you know, plus the weight of the ladder. So you have this plus a small one this direction is going to equal. So that's going to spin the ladder this way. But hey, this force up against the wall is going to prevent that spin. But at some point, this moving far enough away, this number is going to get bigger than this number. And then you're going to have a ladder that falls. So the moment gets bigger than this moment. All right, hell yeah. So let's start to tackle this problem. And I think I can just use this picture right here. We're going to have this reaction at B. We're going to have this reaction AY, but we're going to know that that's going to be equal to 0. So that one we can just, you know, we don't even have to actually include. We're going to have this reaction AX, and then we're going to have the center of mass is going to be 0.5 meters, so the hypotenuse is 0.5. This is going to be 2 meters using the 3, 4, 5 triangle. And then we're going to say this distance for the 90. So this is going to be 900 newtons. Should we use... yeah, I think it's safe to use gravity as 10. Might as well. You could always go through and then use gravity as 9.8. I'm going to use gravity as 10. And then, I don't know if... yeah, I should be able to check this answer with the back of the book. Okay. So we're going to sum the forces. I guess we have this... the center of mass of the ladder is 200 newtons. So we're going to have 900 plus 200, so we have negative 1100 newtons down. And then we're going to have the up component. So we have to get, like, what did we say? I got to draw this again. Draw a small triangle, and then do a 90. And then if this one's the 3, 4, 5, this is going to be the 3, 4. So, so we're going to draw this, and then this, and then this. So this would be the 4, this would be the 3. So I'm going to draw the components. So we have bx, and then by. And this is 4, and this is 3. Cool. Because I want the y component, which is going to be 80%. So it's going to be plus 0.8b. Okay, that's the only other components. So these two components down, 90 and 200, gravity is acting on the person and the ladder. And then this is 0. And then so just this component at this point B is going to be up. So this is going to be 0. Might as well solve for B right now. Holy hell. So we're going to have 1100 divided by 0.8. So B is 1,375 newtons. Okay, now we're going to sum the... so that was the forces in the Y. We're going to sum the forces in the X. It's just going to be BX. So we're going to have 60%. 0.6B in the positive direction minus AX. And so minus AX is equal to 0. So AX, well, I guess just AX is equal to 0.6B Cool. And, oh yeah, we know what B is. Sweet. So AX is going to be 0.6 times 1375. That's going to be 825 newtons. Okay, so now we sum the moments. I'm going to sum them about point B. So we're going to sum the moments about B. That's going to be equal to 0. So we're going to have this weight of 200 newtons. So so hey, this weight's going to be positive, the guy's going to be positive, and then this one's 0, and then this one is the only negative one. Cool. And so I'm going to set it up where the positive ones equal the negatives. All right, so we're going to have 900. Oh, and then so we have to go from point B. Oh, maybe we don't want to sum. Like, I was just figuring, like, where does it really matter where we sum the moments from? I don't think so, as long as it includes x. So I guess we are going to sum the moments at point A. I think that makes the most logical sense. And if we sum the moments at point A, we do have a perpendicular distance to this value at B, and so we can say that's going to be, and that's going to be negative, so we got negative 2B. And then we have the weight of the ladder, which is has a component this direction, so we need to know this distance, and that's going to be that 80%, 0.5 times 0.8 plus 1.6. So that's going to be 2 meters. So now we're going to have, and that's going to be plus 200 times 2. So we have 400. And the units on these are Newton meters. Okay, and then the guy is going to be a distance x. And it's going to be 80%. So we're going to have plus 0.8 x times 900. So 900 times 0.8, and we're going to have 720x. Cool. And that's going to equal 0. So I just summed the moments to be 0. So I from this point, I said, hey, I go up to B. Hey, that's going to be in that direction. It's going to be a negative torque of 2 times the force at B. I go up to this one, and it's going to be in that direction. I see its perpendicular distance is going to be 2 meters across, because 80% of 0.5 is 0.4. And then we go to this distance, which is going to be x which is 80% of x. It's not this full distance. No, it's just x. Holy Toledo. My bad. No, it's not 80. I was thinking about this. I thought x was going to be this distance. But no. X is just this distance from the wall. So my bad. It's just going to be 900x. I'm glad I caught that. All right, sweet. So we know what B is, and so we can just solve for x. So let's do at least 900x is equal to 2b minus 400. So I just got those things over there. And now I'm going to say what B is. That's going to be 1375 times 2. And so we have 2750 minus 400 is equal to 900x. 900x, let's do that, minus 400 is 2350. And then we have x is just this divided by 900. All right, so x is 2.61 meters. All right, sweet. And nice. And we could go back and do this with using gravity as 9.8, which we probably should have done right off the bat. But yeah, let's kind of look this one up. 4.46. 4.46. The distance is 2.61 meters. And so we got 2.611. So hell yeah. So we did it. And I guess we just did B of this problem instead of A. But yeah, that was useful. I mean, you could solve for the reactions of A and B all the way up to x is 2.61. I mean, you could get an equation for that as a function of x. So that's kind of interesting. All right, we're going to do that. I mean, because I don't think a lot of people, especially if it's just like, hey, find the magnitudes at this value. Well, I mean, from the problem, couldn't we find the magnitude of A and B, the reactions at A and B, at all values at x? You know what I mean? So hell yeah, we can. And so that's what we're going to do. So yeah, let's do that. So we have, and we can take all values of x until x gets to be 2.61. Cool. We're going to have b is this, and we're going to have bx, by. If this is a 3-4 triangle, we go up here. And it's just good to get used to this. You're like, oh, now I remember. This has to be 4-3. And that makes sense. I don't know. Maybe it doesn't make sense. That's why I do that smaller triangle. That's very useful. Going to come down here. We're going to have ay and then ax. And this makes sense. I know the force against the wall is that direction. I know the force up is that direction. And so that's going to be the positive values of these. Same thing with by. I know the force has to be that direction to hold that ladder. Okay, so we're going to sum the forces in the y direction is equal to 0. And so we have, oh yeah, we got to figure out the center of mass of the ladder. And let's do this in terms of variables. So this is going to be, let's do this, little m. So we got little m there, and then we have the guy is big M. This might be a worse way to do it, but whatever. And then so we have this weight is little mg, and this is going to be big mg. Cool. So sum of the forces, we're going to have negative mg minus little mg. And then the upward forces is going to be plus by. Well, I already know that by is 0.8 b, and I know that bx is going to be 0.6 b. So let's put those in right away. So by is 0.6 b. Cool. What am I even doing? No, we're summing the forces in the y. So we got 0.8 b. All right, and then we have right here we have plus ay. So we're trying to get ay as a function of x. Right now we have ay as a function of b. Cool. So just keep that in mind. We're going to sum the forces in the x direction. Those are going to be 0. All right, so we have 0.6 b. And then we have minus ax. That's going to be equal to 0. Then we're going to sum the moments about, some place. The first place to sum them would be about point A. Because if we do that, or maybe not, I don't know. What would be the... yeah, I have absolutely no idea. We're going to have variables of ay, ax, and b. And we'll have 3 equations, 3 unknowns. Oof. So yeah, let's sum them at A, I guess. Yeah, and then we'll kind of have that same deal going on. Oh, and then, yeah, that's a good place to sum them from point A, because then our distances from A will be in terms of x. So let's do that one first. So we're going to have positive mgx. So the weight of the guy, distance x. Alright, so now we're going to have the weight of the ladder. That's going to be minus, this is going to be what? 2.5, but we're going to have 80% of that. So 0.8 times 0.25, that's 2. Should have remembered that. And so we're going to have minus 2 mg. All right, now B we can just use B. We don't have to do B into 2 components. You know, one this way and then you know, one up and then one this way. We can just say B is 2 meters. So it's going to be a negative torque. So okay, well, oh, my bad. So the guy is a positive torque. The ladder is a positive torque. But B, this reaction at B is negative, and we're going to have minus 2 meters times B. Cool. And the only reason I'm keeping B as B is because the direction of B never changes. The magnitude will, but the direction of B won't. Where AX and AY, if we said, hey, these are going to be a component in a certain direction, well, that will change. So individually, these will change from, you know, this will go from, you know, weighted to nothing. And then this one will go, this one will always have some sort of force on it. Even when the ladder starts to move, if it's a dynamics problem, you're always going to have a force up against the wall. If you didn't, then it would be able to travel through the wall, you know, as it's falling around this pivot, like it would. Yep. Okay, so we have, so we did B, and that's it. So and that's going to be equal to 0. Okay, so now we have 3 equations, 3 unknowns. Here's an equation. Or 1, 2, 3, and we have B, AY, and AX. Those are the only 3 equations. So now we just need to figure out what we want to solve for. Yeah, I have no idea. I feel like, yeah, my brain is kind of fried right now. Huh. Holy hell, I was so glad I took a pause because I was about to just start summing moments about other points. But no, what we want equations for is the reactions as a function of x. So this one is, you know, we have B as a function of x. Then we can throw in this B into here, and then we'll have AY as a function of x. And sorry I didn't put 0 here. So yeah, let's do this one first. So let's, I don't know, let's get this B over here. So we're going to have plus 2B, and then kind of see what we got going on. And then we're going to divide by 2. So let's just do this all in one step. We're going to have B, the reaction at B is going to be these 2 divided by 2. So we're going to have 1/2 mgx plus mg. Okay, hell yeah. And if we wanted to, I mean, I guess you could factor out the g, where you'd have g, and then you could have 1/2 m plus m. No, 1/2 mx. Yeah, let's just leave it as that. Cool. All right. So now we're going to plug this into here, and so yeah, let's just do that. So we have negative mg minus mg. I'm just following along, and then we got 0.8 times this. So 0.8 divided by 2 is 0.4. So sometimes it's easier to do this in like 2 parts. If I need to multiply this by 0.8, I mean, I can just do that as a side. So 0.8b is going to be 0.4 mgx plus 0.8 mg. Cool. So now I can just throw it in. So we have negative mg minus mg, and then we're going to have plus 0.4 mgx plus 0.8 mg. Whew. And then plus ay is equal to 0. Okay, so now I can just solve for this. Can I, so we have this is negative 1 and this is negative 1. So we have negative 1 plus 0.4. That's going to be negative 0.6. And then when we add it over here, we're going to have 0.6. Oh, my bad. No. This is mg, but this is mgx. We cannot add those terms, but we can add negative 1 to 0.8. That's going to be negative 0.2 mg. So over here, we're going to have minus 0.4. Let's write this again. Ay is minus 0.4 mgx plus mg, and then plus 0.2 mg. Because on this side, this was negative 1 plus 0.8. That's negative 0.2. On this side, take it to the other side, is plus 0.2 mg. All right, sweet. So we're good there. So that is an equation for this reaction just as a function of x. And then we'll take this into, well, I mean, we could put this into our calculator. Let's probably just do that. I mean, we could do this in Excel as well. Here's an equation for b as a function. And then, so now we just do this. So let's do 0.6b. That's going to be 0.6 divided by 2 is 0.3 mgx plus 0.6 mg. All right, and then, and that's what ax is. So sweet. So we have ax. So bring this to this side is just this. It's 0.3 mgx plus 0.6 mg. All right, sweet. And if we did this right, hopefully, so now we're in our calculator. What I want to do is I'm going to throw in 9.8 stored as alpha g. So that's going to be gravity. I'm going to have little m 20. Yeah, I'm gonna. What should I store big M as? I think I'm gonna store big M as W. All right, change batteries. We're back. So yeah, the guy's weight we're gonna put in as 90, stored as alpha W. So for this, W in my calculator is gonna be that mass M. M in my calculator is gonna be the little m. G is gonna be the gravity. And I think that's it. And x is our variable. Okay, so we're going to do b first. 0.5 alpha w alpha g x plus alpha m alpha g. All right, next one. We're going to have ay, because this is the one that's going to go to 0 at. So yeah, this is the one we're going to try to figure out if we did it right. So we got negative 0.4. Alpha w alpha gx plus alpha w alpha g plus 0.2 alpha m alpha g. All right, now we got this one. 0.3 alpha w alpha gx plus 0.6 alpha m alpha g. All right, so let's graph these. And I'm just going to do a zoom fit just to kind of see where we're at. So that first one is this. AY is that second one. Okay, so all this is going to happen, it's in terms of x. So yeah, x can't be more than 3. So we're just going to go window x from 0 to 3. We'll do negative 1. Negative 1 to 3. And then the reactions are going to be, you know, in the thousands. So we're just going to do negative 100 to 2,000. And then kind of graph that. Alright, sweet. So the second one, we want to find the 0 of this line. And hopefully this is 2.61. If it's not, then we did something wrong. This says it's 2.46. I'm going to store 10 stored as alpha g. Yeah, so I think we did something wrong because alpha y, when this is 0, our distance x should be we just solved it, 2.61. So this is the bummer about doing problems, because you're just like, ah, shoot, you know, I thought I did it right. So yeah, we're going to do a left bound, right bound. But it's just difficult to get it right the first time. So we definitely have an obvious mistake. So let's go back and see if we can start doing it again. But before you just start redoing the problem, you know, maybe you can kind of find your mistakes. So we're going to sum the forces in the y. So we're going to have, and let's do this. So we have alpha w, alpha g, 900. And then this thing is going to be 20. Did I put m as 20? Alpha m? Oh, I didn't even store alpha m as 20. So sorry about that. Store it as alpha m. So yeah, my bad. So now we should be good. So we probably did everything right. I just didn't store my values. So, but that was cool to have a place where I could go just to make sure. So we're going to do a value of 2.6. We're going to go 0. So hell yeah. So now we're probably just in. Yeah, so we didn't make any errors at all. And so I can do 9.8 stored as alpha g. And then graph that. And we can actually get the value of x for 9.8. And yeah, let's see if it's, so we're going to go value 2.6, 0, left, whoa. Alright, left bound, right bound. Alright, same, yes, it's almost exactly the same. Okay, sweet. But yeah, now let's take a look at kind of what's happening. So when the dude is just like right on the ladder, what I was expecting is that this would be AY. This would be about 900 newtons, you know, and you know, because maybe the weight of the ladder is taken up by B, and then so is that what we have? So we're going to go value of 0 when x is 0. Yeah, this weight right here at A is going to be 900. But plus a little bit extra. Now the weight of the ladder is 200 newtons, but we're only taking another 20 newtons, 920 newtons when the guy is standing right here. Most of the weight of the ladder is taken by B, and so we can see that B is the blue line, and 196 newtons is being taken by B. Now B is in this direction, so BY is 0.8B. So if we did 196 times 80%, or 0.8, so let's do that. 196 times 0.8, we would get 156.8. Now let's go back to our graph at 0. And so if we go to AY, we have 921.2 newtons. And those should equal, holy hell. Oh yeah, 156.8 newtons plus 921. Yeah, so yeah, these should equal 1100. 156.8 plus 921.2. And it's 1078 because I'm using 9.8, which is 90 plus 20 times 9.8. Yep, so that checks. I just switched my alpha, I switched my gravity to 9.8, not 10. So it's not 1,100 pounds, it's 1,078 pounds. Alright, but this is cool because, instead of just asking one problem, just asking one question, like what's the reactions of A and B at x.5, we did them from all. So let's actually go and, I actually never solved the actual problem I'm supposed to. So at 1.5, we have B, this reaction at B is going to be 857.5 newtons. So 858 newtons. That's going to be B at 1.5. X is equal to 1.5. Alpha, what do we have? Alpha Y is, so AY is going to be 392 newtons, and then AX, the up against the wall, is going to be 514.5 newtons. And so you can see when the dude's standing right up against, like right here at 0, you do have a reaction against the wall. It's not because the guy is standing right there. That guy actually is generating no force, no reaction up against the wall, but it's the fact that this ladder has weight. Is this component does have a, if we take a perpendicular section, hey, this weight of the ladder is driving the ladder into the wall. And so if we take the guy out of the equation, let's do that. So if alpha W is, 0 stored as alpha W, and now we graph it, when X is 0, the weight, there should still be some weight against the wall. So we're going to go 0. And what we have is, we have 117.6 newtons of force up against the wall. So now we're going to throw in 90 stored as alpha W and then graph that. And this value shouldn't change just because the guy is standing right at X equals 0. So we're going to go value 0. And yes, it's 176. So that's that brings up like a material mechanics problem of, if you have a bridge and you kind of have these supports of the bridge and then a beam, and you're just like, if you put your weight in the middle, hey, a couple of things happen. The bridge bends. This side and this side have to take half the force. But then if you have that same bridge and you put all the weight right up against this support, well, a couple of things happen. One is that the bridge doesn't bend at all. Okay, so you don't have any of that. And this side of the bridge doesn't see any force. It doesn't even know that there's a force over on this side. It can't even tell. So that's kind of, so some of these statics problems kind of have those positions. So I definitely wanted to point that out. Alright, so this was pretty cool. I mean, I wanted to just take a couple minute video and just talk about, how to take a free body diagram and put it into outer space. But I guess I just ran into the issue when it comes to, I think it's very simple to do when it comes to like moving this way and this way. But when it comes to actually the thing rotating and preventing rotation, for whatever reason, I think that's where I had to take a pause and start explaining. And so now we have a longer video. So, hell yeah, I don't know what I'm going to do, if I'm going to put something at the beginning of this or just leave it as is. Alright, hell yeah, I totally forgot to even check the back of the book for the reactions at that 1.5. So we got 4.46. Alright, booyah. Alright, 4.46. We have 647 newtons, that's at A. And then we have 858 newtons, that's at B. Alright, sweet. So we're going to pull up our graph, value 1.5, and we have 858. And then we have, we're a little bit off. 647. Oh, no, because it's the total reaction. So it's so they got 647. Yeah, because we got 514.5 and then 392. And this is cool because it brings up Pythagorean's theorem. So yeah, we have this reaction at A to be this is AY. This is the red. And then, so this is 392, and then this is 514.5. All right, sweet. And so we're going to be going, and it's a vector. It's kind of cool. It's like, hey, we're going to go up 1, 2, 3, 4, and then over 1, 2, 3, 4, 5. So that's kind of the direction. And, oh, now I'm even curious, because the other thing that I was thinking is slipping occurs when this reaction, no, never mind. It occurs when this is 0. And then your reaction is totally that direction. I was thinking it also had something to do with the direction of force up the ladder, but I guess not. But anyway, so the components of this are going to be up 4 over 5, and so that's going to be, so you have 392 and then 514.5. Now it's a triangle, and here's your components. So how do you find the hypotenuse? Well, you're going to square this plus the square this and then the square root of both those. The other thing that you can do is kind of know that if I have a triangle where both these sides are the same, then the hypotenuse is only going to be 1.4 times the larger number. And if I have a triangle where one of the numbers is 0, so let's say I have 500 and then the other number is 0, well, your multiple is just of 1, you know what I mean? So if I know both these numbers, I can just take the max. So we have basically 515 times 1.4. I know that the total resultant can't be greater than 724. And it's because these aren't equal, and so it has to be less than that. And so then you just get better at guessing, you know, your multiple, 544.5. I'm just going to guess a 1.2 multiple. 515 times 1.2 and 618. Now how close would I have been? Well, I'm a little bit off. So yeah, if these are fairly close, you're going to be kind of, so it's going to be like a 1.3 times 514. Yeah, so it's going to be like 1.28. So I like to think of it as a multiple of what the hypotenuse would be if both these sides were the same, because you are dealing with a vector and a triangle. But anyway, so let's just do it. It's this squared plus this squared, square root that. So we got the square root of 514.5 squared plus 392 squared. Booyah, and that's 646. And let's write another. Let's write one more in our equation, because we said that blue was the reaction at B, red was the reaction at AY, and then black was the reaction AX. So let's do the square root of the red one squared plus the black one squared. And then that'll give us an equation of the reaction at A in terms of just its magnitude. And that'll be pretty cool. So we got negative 0.4 alpha W alpha G X plus alpha G alpha W plus 0.2 alpha M alpha G. Okay, square that plus 0.3 alpha W alpha G X plus 0.6 alpha M alpha G squared. All right, I'm just going to double check this. So 0.3 WX GX, sorry, plus 0.6 mg. Negative 4 WGX WG. Okay, sweet. So we're going to graph that, and that should give us our 647 at 1.5. So this is the reaction at A, and cool. So we're going to get the value at 1.5, and we get 647. All right, so sweet. So I'm glad I made that little addendum. And I don't know, it's just kind of cool to look at this, because we got a value of 2.6, and that's where it's going to slip and tip. And then so this reaction at A does get bigger. It's all in this side, but it does have a minimum. So that's kind of interesting, is that at some point this reaction at A is going to be the least. Do you think that's going to happen at 1.6? Let's find that. Just because we want, that's the whole point of doing these, is like, hey, can you learn anything else from this problem? Maybe make up your own problems. All right, left bound, right bound. and we got 1.5. So this reaction at A is when X is 1.5, so a little bit less. So that's kind of interesting. But yeah, it's probably because the ladder is also, I don't know. I don't know why that is. But yep. Alright, so I think I'm done with this. Thanks for joining me on this one. And guess what? That's a video.